And we'll have 2 days on 8-2. Then we'll have 2 days on 8-3, and then we'll be testing again already next week. So make sure that you're keeping up with everything. Don't take tomorrow off. Watch the video. There's basically 6 days of learning that you're going to be tested on. So missing one of those days would not be a good thing. So the reciprocal function family, I started to show you on the graphing calculator how these graphs look, and we did a little bit of graphing on the first day with inverse variation. So now we're going to graph reciprocal functions. I'm not sure that we'll get to the translations. I made the video yesterday expecting that maybe we wouldn't, so we'll see whether or not we make it all the way there or not. Down here. For a class party, the students will share the cost of the hall rental. Each student will also have to pay $8 for food. The cost of the hall rental is already graphed. What effect does the food cost have on this graph? What would happen? So I look at this and I see we've got a number of students here, and this is the cost per student. But this is without the food. So we're going to be adding another $8 onto this cost for food, which in this graph means we're going to go another $8 up. So that would translate this graph $8 up. So it was a nice little graph before. You realize that if you got a lot of people to go, the cost of this hall rental was going to be really low. And then here came the food. Because, you know, what are you going to do in that hall for all that time? You're going to eat, hopefully. Maybe this is a prom thing, dancing, those type of things. And there's a cost that's equated with that. And like we can see, the hyperbola branch shows us that the more people that go, the less the cost is going to be for the hall rental. But the $8 is everybody pays it, no matter what. So that would be a translation of that graph. Now, what we have to do is just look at basics here for our graphs. And functions that model inverse variation are what we've been studying and taking a look at, along with other forms of variation. Those have the form f of x equals sum k over x. So that we already know. And x can't be 0 because you can't divide by 0. Now they belong to an entire family of graphs that have a parent function, and these are called the reciprocal functions. That have a little parent function, f of x equals 1 over x. So, quick reminder, parent functions are supposed to be the easiest one of that type of graph. So notice, this isn't fancy. We just put a 1 over x. I mean, it just has to show the division. That's it. And that's going to be our parent function. Like it says, x can't be 0. We already know that. But what that does, x not being able to equal 0, creates a vertical asymptote. Again, asymptotes are lines that we can approach but never touch. It's never going to get to 0. Because we know we can't divide by 0. That doesn't exist. So if it doesn't exist, that's where our vertical asymptote is going to be located at. And we've talked before about asymptotes and how important it is with asymptotes to get those on there right away. And then don't cross them. Vertical asymptotes do not get crossed. Alrighty, our essential understanding. We are eventually going to get to transformations because the parent is 1 over x, but the numbers are going to change. So we have to know what the basic looks like, and then we have to know how to make changes to it. All right, transformations of the parent reciprocal function include all the things we've talked about this year. Stretches and compressions. Compressions are also called shrinks. Could be reflections, horizontal and vertical translations. So, key concept here. The general form of a reciprocal function family. we are really going to like this one. Star it, underline it, box it, circle it. Y equals A over X minus H plus K. So that's the general form. The general form of a member of the reciprocal function family is Y equals A over X minus H plus K, where H and X can't be the same thing. Because if they were, 3 minus 3 would give us 0 in the denominator. So that's where we're going to find our vertical asymptote. The inverse variation function Y equals A over X, so not a 1 anymore, shows us that this is where we're going to find reflections, if there's a negative. We're going to find vertical stretches. We're going to find vertical compressions, because that's what A has always told us. So stretches, shrinks, reflections are all a part of A. The graph of the parent reciprocal function is right over here. Now, if they didn't give us that, it wouldn't be too hard to get. Because we know it's Y equals 1 over X, and we just need to put a few numbers in. So if we put a 2 in, we'll get 1/2. A 3 in, we'll get 1/3. And if we want to see what's going on with the negatives, we could put in a -2 and a -3 and get -1/2 and -1/3 and get that graphed. So 2 1/2 right here, 3 1/3 right there, and -2 -1/2 and -3 -1/3. Go ahead and make sure attendance is updated here. I didn't stop for that yesterday, and I had to email and get some changed. Got to start coming to class on time, folks. If you can't get your breakfast and get here on time, then you don't get breakfast. Come to class. Problem 1, graphing an inverse variation function. What is the graph of Y equals 8 over X? Identify the X and Y intercepts and the asymptotes of the graph. Also state the domain and range of the function. Whenever they do their updates, something happens with these graphs. They lose all the blue. I don't know how that happens. Alrighty, so I know what it's going to look like. It's going to be a couple of little branches, but I want to make a table. After I think about what I should see, this has an 8 on the top of it. That was A, so this is definitely going to be a vertical stretch. Factor of 8. So whatever it was before, this is really stretching out because they're multiplying it by 8. Now, what I want to do is see just how close the branches come in to 0, 0. And if I want to do that, then I would want to see what's happening at the numbers 1 and 2. Because that'll show me what's going on the right-hand side. And here's where we get to the part with hyperbolas. There are always 2 branches. And a lot of students have said in the past, it really helps to just have 2 separate little tables. Because we just need 2 points for each of the branches, and then we can figure out some points and graph them in there. All right, first thing I know is I better put on my vertical asymptote at x equals 0, because down here, if this is 0, that's bad news. So I'm not going to write vertical asymptote out every time. I'm going to go with VA. X equals 0. Now vertical is up and down, so x equals 0 is right here. So this graph is never going to touch the y-axis. Now let's put some points in. Well, all I have to do is take 8 and divide it by my numbers. 8 divided by 1 is 8. 8 divided by 2 is 4. That'll give me 1 branch. 8 divided by -1 is -8, and 8 divided by -2 is -4. That'll give me the other branch. So 1 8 and 2 4. And I know what it's going to do. It's going to make a nice curve in the first quadrant. Because the other asymptote that this is going to have is y equals k. And that's a horizontal asymptote. And if you're thinking, well, this one doesn't have a k, you're absolutely right. Notice how there's no plus or minus behind it? So it was a 0. It didn't do anything. So it's going to be y equals 0. So HA, y equals 0. Now we can get the other branch on at -1, -8, and -2, -4. So if it's really basic, and it's just y equals a over x, we're always going to have the x-axis and the y-axis as our two asymptotes, y equals 0 and x equals 0. And then we just have to find a few points to know how close is this going to come into the origin. Now the reason I'm looking at that is because my 8 was supposed to be a vertical stretch. So if I'm multiplying by 8, it should not come in very close to the origin. It was supposed to be stretched out 8 times what it was. So we've got a table, we put the asymptotes on there, we graph the points, and we get down to the questions they wanted us to answer, which is x and y intercepts. That's where it crosses the x and y axis. Is our graph ever going to do that? So we don't get any. We better put none. Because if we leave it blank, that might mean we just don't know what we're doing. We want to tell people there aren't any. Our asymptotes or x equals 0 and y equals 0, because there wasn't an h and there wasn't a k. Now, domain and range. Domain is where we say there's one x value we're never going to use. What x value did we never reach? 0. Notice it's the asymptote. And then what y value for the range are we never going to get to? Exactly. So if there's no h and k, this is pretty standard. This is what we're going to find out for x and y intercepts, asymptotes, domain and range. Going to look at a lot of little basic graphs like this today. Looks like people are still writing like crazy, so I'm going to hang on here a second. Did it not have the prompts in your packet? It didn't? Oh, okay, so you had to write those down. Anybody need more time? Alrighty, y equals 12 over x. Is that a vertical stretch or a compression? Huge stretch. Factor of 12. Vertical stretch. Factor of 12. So this one should really pull away from 0, 0, because that's what the vertical stretch was doing in the graphs before. Try and get the blue lines to show up again. Alrighty, how about asymptotes? Do you see a plus anything down here or minus or in the back? So where are the asymptotes? Yep, 0 and 0. So x equals 0 and y equals 0 again. And again, I would want to get those on right away. Asymptotes are lines that we approach but we don't cross. And then a couple of little tables. Again, all we need is about 2 points from each side of the x-axis. But if I put a 1 in this time, I'm going to get 12. and that's not going to fit on my graph. So I'll start with 2 this time instead. Would 3 be another good number for 12? Well, then let's use 2 and 3 and -2 and -3. 12 divided by 2 is? 12 divided by 3 is? And then just put some negatives on there, and you have the other branch. So let's graph those. 2, 6, and 3, 4, and -2, -6, and -3, -4. Well, that's not getting anywhere into 0, 0. Was it supposed to? There's a 12 up there. This is really going to stretch away from the origin. But we again know it's a branch, and it's supposed to approach the asymptotes but never cross them. So we get that in there. X and Y intercepts. What are we going to put? There aren't any. Yeah, it's not going to cross. Domain, what do we leave out? X can't be 0 because it's a vertical asymptote. Range, what do we leave out? 0 because it's a horizontal asymptote. We do everything. What is the graph? Identify the X and Y intercepts, the asymptotes, state the domain and range of the function. Done. Been there, got the t-shirt. Now, B says, would the function y equals 6 over x have the same domain as the other two that we just graphed? What do you think? Yes? Well, how come? No h's, no k's. It's exactly the same. So, yeah, domain and range would stay the same. Each part that we have graphed, and you've heard me call it this, each part is called a branch. We can't call it a line because it's not a line. They're curved. That's the big part of it here. So it's a branch. And the branches of the parent function y equals 1 over x are going to be in quadrants 1 and 3. We also know they might throw a negative up there in the top. What is a negative done for us all the time? Flips it. It's a reflection over the x-axis. It's the same thing here. It's not new. So if we do have those negatives, stretches and compressions, those aren't affected by it. They're going to be in the same quadrants. But reflections, those are going to make our graph go in quadrants 2 and 4. So those are things we can know about it just by looking at the equation. You know, we don't have to do any fancy math to see that. So now, this one says, let's identify reciprocal functions. For each given value of a, how do the graphs of y equal 1 over x and y equals a over x compare? And what's the effect of a on the graph? We're not going to graph them, because I think that's silly. I think we already know what's going to happen. So if we're supposed to start with this, and we're supposed to change that number on top to a 6, what is that 6 going to do? It's a vertical stretch, factor of 6. Is it going to be close in to the origin? A 6 is going to pull it away. So it is going to be pulled away from the origin. .25. I don't think I like that. When they do decimals, they're usually trying to hide something from me. That's 25 100ths. What is 25 100ths reduced to? That's what they were trying to hide from me. They didn't want me to see that, because then I could tell them this is a vertical compression, factor of 1/4. They were trying to be sneaky. Now wait a second though. All the ones we've done so far took the graph and stretched it vertically. A compression, doesn't that go the other way? So is this going to be pulled away from the origin more or pushed in? It is pushed in toward the origin. So fractions, again, are vertical compressions, which I always talk about in first semester, how if your function is made out of rubber bands, vertical stretches, grab onto it and pull it vertically. And then if you have a vertical compression, then you have to squish it down. And that's what's happening here. Oh, this one. This looks like it might be a bit of a challenge. This is a two-parter. What's the negative doing? Reflect over the x-axis. What did we say the 6 was responsible for? Vertical stretch, factor of 6. Now, that's 6. Pulled away or pushed in towards the origin? Pulled away. But a bigger deal would be the quadrants. So 6 over x was in first and third quadrant. What's negative 6 over x going to do? Yep. Quadrants 2 and 4. Now, here's the part where I didn't exactly know where to make your video for tomorrow, because when we get here to got it 2, I thought, do we even need to write this one down? How are you doing? Feel like you got the vertical stretches, compressions, reflections, and all of that down? Well, then let's just talk through these real quick. What's a 1/2 on the top going to do? Vertical compression, closer or farther away from the origin? A 2 on the top. Stretch, closer or pulled away? Negative 1/2. Vertical compression, negative is going to do what? Quadrants 2 and 4. So, yep, you've got it. We don't need to do that one. So on the video for tomorrow, I already did this part, but we're going to go ahead and talk through it because I know you don't want to watch long. It wasn't a long video anyway. It's only 25 minutes, but how about we take a little bit of that off by going through one of these? We can translate our reciprocal functions. Of course we can. We can slide them up, down, left, right. That's what translations are. So translate any reciprocal function horizontally or vertically, just as we have any of the others. And then we realize, well, that's h and k. So now they're saying instead of just being something over x, they're actually going to put some other numbers in there. So here's our parent function, y equals 1 over x, where we know x can't be 0. We've already talked about a. If a is a value greater than 1, then it's going to be a vertical stretch. Fraction between 0 and 1, a compression or a shrink. And a reflection, we know when there's a negative there. Now, what if we look at it and it's not just y equals some number over x? That means it's been translated. Notice that x minus h, so that's still going to be the opposite of whatever we think should be there. When it says x minus 3, it actually moved 3 units to the right. But k in the back here, that's still normal. That's our up and down. So when you combine all of this and you put both the h and k together, you get that y equals a over x minus h plus k general format that I was talking about earlier. Now, usually, not usually, we're going to switch that. Make this a capital I. No matter what math you go into, when you start talking about reciprocal functions, and reciprocal functions are a huge field, by the way. They're called hyperbolic functions, and in college there's a hyperbolic functions 1, a hyperbolic functions 2, and a hyperbolic functions 3. There's a lot that you can do with these. You always graph the asymptotes first. So let me get the blue, and then we'll start talking about the general form and what we know for h and k. It's amazing how it's doing that. I wonder if I can get the tech people to fix that. Alrighty, so here it is. And there's the general form so we don't miss something. Always a good idea to write down the general form so that you know, hey, this is different. Well, the first thing we want to do are asymptotes. The vertical asymptote is always about the x's, because if you draw any kind of vertical asymptote, think of a gigantic Cartesian coordinate plane. You've got your x-axis and your y-axis. When you draw those vertical lines, you're karate chopping the x-axis. So that's how they get their name. X equals something. And we're always looking here, right here. That's going to tell us what number is out. What number is bad down there. Yes, and notice how it's the opposite of what we see, because we look up here and see a +1, but it's not. -1, that's our vertical asymptote. Horizontal asymptote, that's the normal one from the back. So it's y equals what in this one? That's okay. Let's put them on there. X equals -1. And y equals -2. Oh, well, that's interesting. What it's really done is it's kind of moved the origin for this graph. Do you see that? Where we used to have everything centered at 0, 0 by not having an h and k. Now everything is going to be centered here. We still graph like normal, but we have to know that because I need to make a little table for my graph. In fact, I want to make my 2 little tables. And here's where we're going to get them. We want to pick x values that are close to that new little origin. We want to see what's happening just to the right, which would be over here, and what's happening just to the left. So for my right-hand side, I'm going to pick 0. I want to know what it's doing right there. And 1. Our vertical asymptote, we go to the right side, pick 2 numbers that are really close to that. So likewise, we want to do that to the left of this. So what would be some really good numbers for this one? -2 and 3. We're at -1. -2 and 3 would be great. Now we just have to plug them in. And where do we plug them in? Right back here. So let's put a 0 in. 0 plus 1, because whenever there's more than one term on the top or the bottom, you have to do that first for your fractions. 0 plus 1 is 1. 1 divided by 1 is 1. 1 minus 2, -1. Put a 1 in. 1 plus 1 is 2. 1 divided by 2 is 1/2. 1/2 minus 1 minus 2 is -1 1/2. Sorry, doing the math in my head already and talking about the answer. A -2. -2 plus 1 is -1. 1 divided by -1 is -1. -1 minus 2 is -3. Put a -3 in. -3 plus 1 is -2. -1/2 minus 2 is -2 1/2. We've got it. 2 points for each branch. We should be good. So 0, -1, 1, -1 1/2. That's really close into our origin, isn't it? To our new origin, I should say. We should have known that beforehand, right? What number tells us this is going to be pretty close into the origin? Exactly, this one up here. This tells us, hey, this is going to go in pretty close. -2, -3, and -3, -2 1/2. And there's our branches that don't cross our asymptotes. There they are. So domain, what number's out? An x we never use. It's not 0 this time. Good, -1. So x can't be -1. It can be everything else. What y is out? See how it's always the asymptotes? Yeah, so we can't use x of -1 because that's an asymptote, and we can't use y of -2 because that's an asymptote. So, tomorrow, when you watch the video, you'll be able to fast forward through this one. And hopefully that way, when you do the second one, you'll be like, I already feel like I know how to do this stuff, and you can do the got it from there. But that's where I'm going to quit today. Like I said, I kind of thought we'd get through all of this, but you guys were much faster and better at it. So, there we are. And of course, there's going to be some graphing, so I'll bring around some graph paper while you're writing that down.